So good afternoon, everybody. This is the legacy of the Hubble Space Telescope, how it went from being a white elephant to being a white knight. And there could be very few people who don't recognize the Hubble Space Telescope. If you show this picture not simply to astronomers, but show this picture to, I would argue, the man in the street, you will probably still get a hint of recognition of what this instrument actually is. What I'm going to be covering today is an introduction to the need for space telescopes and ground-based alternatives. I'll be looking at the history, how the mirror was flawed and how the optics were fixed, and then looking a little bit at the legacy, the scientific legacy, and how it touched the public consciousness along the way. And then I'll finish with a revamp of the introduction, again thinking about the need for future space telescopes, and again whether there are ground-based alternatives. So if we look at a comparison of telescope mirror sizes, this is quite a useful way of just gauging how telescopes have got so much larger. These are all to the same scale, and the scale you can see in the very bottom, tennis court and basketball court, gives you an idea of size. But the lens in the very top left is the Yerkes 40-inch refractor, and you can see how large telescopes have got over the last 100 years or so. And there are some true monsters coming along in just a few years' time, such as the European Extremely Large Telescope. The largest in the world at the moment is the Gran Telescopio Canarias, this one at the top here, with a diameter, if you can call it a diameter when it's hexagonal segments, a diameter of about 10 meters or so. So if we have telescopes like that, it's sobering to remind ourselves that space telescopes, which are in the bottom left-hand corner of this particular diagram, we can see that space telescopes by comparison are substantially smaller. The Hubble Space Telescope, you can see here, with a diameter of 2.4 meters, is very small compared to all of the telescopes that we can see that are the current ground-based generations. And I'll be saying something more about Kepler-Gaia and James Webb at the end of the presentation. So, of course, telescopes have come a long way in the 400 years since Galileo, and we know that lenses in refracting telescopes have given way to mirrors in reflecting telescopes as of about a century ago, because lenses bigger than about a meter are impractical. And there's always this quest, this drive to have telescopes with larger and larger mirrors. And that's driven by two factors. One is that the larger area collects more light, so we can see fainter objects, but also larger mirrors will have a higher resolution, so we'll see more detail, which means either we'll see smaller objects or we'll see similar objects at a greater distance. So if we've got large telescopes and ever larger telescopes appearing on the ground, why put such a small telescope into Earth orbit? And the answer, of course, is to get away from the blurring effects of the Earth's atmosphere. So by placing a telescope above the atmosphere, we can get the full resolution that the mirror is capable of, whereas if we have the same telescope on the ground, the resolution will be distinctly worse because we're looking at the chaotic turbulence of the Earth's atmosphere. And the limiting size of 2.4 meters for the Hubble, it would be great to have a larger telescope in orbit, but the 2.4 meters of the Hubble was dictated by, that's the largest telescope you could fit into the cargo bay of the shuttle, which is what was used to launch it some decades ago. If we think about the resolution of the Hubble Space Telescope, if we compare that with the telescope of the same size sitting on the ground, having to look through the Earth's atmosphere, the resolution would be 10 times worse on the ground compared to the resolution that can be achieved when you're above the turbulent effect of the Earth's atmosphere. So a factor of 10 is well worth having. What about the history? Where does the story of the Hubble Space Telescope start? Perhaps a little bit earlier than you appreciate. Even when men were still walking on the moon, NASA were thinking about a large space telescope, simply called the LST at the time. And the second milestone in the history of the telescope? Well, the second milestone was its cancellation. In 1974, Congress withdrew all funding of the project. There was then a little bit of an outcry from scientists, and eventually the scientists got their way and persuaded the funding bodies of America to look at funding a large space telescope, but they could only do this by collaborating with the Europeans. So NASA and ESA got together, and finally it was agreed that the Large Space Telescope project would be funded at the end of the 1970s. The spacecraft construction was tendered out to the firm of Lockheed, and the optical telescope assembly went to Perkin-Elmer. So we might think of the Hubble Space Telescope as being a telescope with some solar panels on the side, but actually, as far as NASA and ESA are concerned, the Hubble Space Telescope is actually a spacecraft. It's a spacecraft that happens to have a telescope inside it. So you can't simply build a telescope and throw it up into orbit. You have to treat it as a spacecraft, which Lockheed are expert at building, and you need to think about the telescope optics, and that went to Perkin-Elmer. So in the late 70s, the construction of the primary mirror began, and Perkin-Elmer produced this 2.4 meter diameter mirror. And in 1981, they finished polishing the mirror and they declared it as essentially perfect, as good as you can get. The most precise mirror ever built was the claim at the time. And it was appreciated that the mirror is, of course, a rather important aspect of the telescope. So when the project was started, it was agreed that there would be a backup mirror. And Kodak produced a backup mirror, and in parallel with Perkin-Elmer produced a mirror of 2.4 meters diameter, completely independently in terms of producing the mirror, grinding the mirror, figuring the mirror. All of that was done independently, such that if anything went wrong with the Perkin-Elmer mirror, there was always a backup. And that was considered prudent on such an expensive project. But once Perkin-Elmer said, we're done, we're finished, the mirror is absolutely fantastic, it was agreed that there was no longer any need to work on the backup mirror, and so at that point the backup was shelved. It was effectively just put into storage, and eventually it went into a museum. Fine, okay. 1983 was the original planned launch date. And at that particular point, the Large Space Telescope was named the Hubble Space Telescope in honour, of course, of Edwin Hubble, who'd done so much work a century or so ago on looking at the recession velocities of galaxies and the expansion of the universe. So 1983 was the original launch date, but that got put back. There were a few delays on the part of Perkin-Elmer, and then there were a few delays on the part of Lockheed. By 1986, they were pretty much ready to go, at which point the budget had hit something like $1 billion and was still going up. But of course, in 1986, there was the Challenger disaster, and the shuttle fleet was grounded for quite a few months, a couple of years or so, and when it resumed flights, the shuttle then had a backlog of satellites to take up, and the Hubble Space Telescope was in the queue and didn't see a launch until 1990. So finally, in 1990, the Hubble gets into orbit. At that point, the construction costs were estimated as something of order $2.5 billion. And that doesn't count the launches of future shuttles to maintain the telescope. One thing I have to say about design, because it's relevant for what comes next. The design of the mirrors in the Hubble Space Telescope is a so-called Ritchie-Chrétien design, which means that the primary mirror and the secondary mirror, as it happens, are both a hyperbolic shape. Now, perhaps you're familiar with the idea of a parabola or a parabolic mirror being used to focus distant light to a perfect focus. And a parabolic mirror is indeed very good at doing that. But the last big telescope, the last world-class telescope that used a parabolic mirror was actually the Hale telescope on Mount Palomar, which has a 5-meter or a 200-inch mirror. Since then, and that telescope was designed in the 30s, built in the 40s. Since then, all big telescopes have used hyperbolic mirrors. A parabolic mirror is great for focusing distant light to a point, but it won't give you perfect images over a wide field of view. It'll give you a perfect star image at the center of the field of view, and then you'll get aberrations as you move towards the edges. To avoid that, people changed from a parabolic shape to a hyperbolic shape, which is very similar to a parabola, but just a slightly different curvature in the shape of the mirror. But it's problematic because a parabola will focus distant light from a star, but a parabola won't. Parabolas are designed to work in combination. A primary mirror and a secondary mirror in combination will produce beautiful star images. But on their own, a parabolic mirror won't focus light to a point. And that's relevant for what happened when they finally got the Hubble Space Telescope in orbit and turned it on a distant object. Slowly, the horror dawned. It would not focus. They were expecting images similar to the one on the left, where the star images are nice points of light, but what they were actually seeing are images similar to what we see on the right-hand side. A lot of the light is focused into a stellar point, but a significant amount, many percent of the light, is distributed in this horrible halo surrounding the star images. So what has gone wrong? They eventually admitted that the only explanation for getting images like the one observed, it's nothing to do with the focus being wrong in terms of the positions of the mirrors. They admitted that the primary mirror had spherical aberration. Let's make sure we understand what spherical aberration is. Let's imagine we've got a mirror here which is supposed to focus light from a distance to a point. So that's not necessarily the true shape of the Hubble mirror. Let's just keep it simple. So light is focused to a point, and light hitting a different part of the mirror should come to the same point focus. But what happens in spherical aberration is that light hitting further and further away towards the edge of the mirror comes to focus too early, as indicated by these red lines. It's called spherical aberration not because you only get it from a sphere, it's just a characteristic aberration that occurs when you have a spherical shaped mirror, but it can also occur for any shaped mirror when the edges of the mirror bring the light to a premature focus. So where do you put the camera? If you put the camera in the middle of where most of the light is focused, you can see, well, almost none of the light is actually focused at that point. What if you place the camera where most of the light is focused? Well, the light hitting the edges of the mirror are coming to a focus before the camera and hence producing that halo, that out of focus halo that we saw in the previous slide. So we're getting spherical aberration. Remember, what we wanted to see was something more like that bottom panel where all the stars are nicely focused and you get essentially no halos around the stars. It was pointed out that, yes, this is a problem, but bear in mind that if this telescope was on the ground and we had a 2.4 meter diameter telescope sitting on the ground, the best we could possibly hope to see through the Earth's atmosphere would be something like that top panel. In other words, we're doing better than having this telescope on the ground, but we're not doing quite as well as we ought to. Well, doing better on the ground is okay, but you've just spent $2.5 billion of taxpayers' money getting it into orbit, so that clearly is not acceptable. How could a mistake be made to actually make the mirror with spherical aberration? Tests were carried out during the construction, during the figuring of the mirror, and those tests indicated that it was the most precisely figured mirror ever made. It had a surface roughness, in other words, the peaks and the valleys, if you think about the overall shape of the mirror, the peaks and the valleys had a roughness of about 10 nanometers. It's difficult to appreciate just how small 10 nanometers is, so imagine taking the Hubble mirror and scaling it up until it's the size of the Earth. That would be equivalent to a surface roughness of about 3 centimeters. Surface roughness of barely more than an inch over an object the size of the Earth. That's how precisely figured this particular shape was. But unfortunately, it was precisely figured to the wrong shape. It was off at the edges by about 2 microns. And if 2 microns doesn't sound like much, remember that's much longer than the wavelength of light. And if you've got a mirror which is not precisely figured to a small fraction of the wavelength of light, then it's not going to focus light correctly. There's a big difference between 10 nanometers and 2 microns. It's hundreds of times larger. Why did the error occur? Well, part of the problem is because the mirror is hyperbolic. A parabolic mirror will focus light from a distant point to a focus, but a hyperbolic mirror is not designed to do that. A hyperbolic mirror is designed to work in conjunction with another hyperbolic mirror. So how are you going to test them? You can't possibly test 2 mirrors at the same time because you don't know which one needs adjusting. So you can test a hyperbolic mirror using what is called a null corrector. It's a piece of optics, it's a combination of lenses and mirrors that is put into the test rig to allow you to test whether a hyperbolic mirror is being ground to the correct shape. But one of the lenses in the null corrector was misplaced in the test rig. People have said a washer was placed on a bolt where it should not have been, and also because that displaced the whole rig by something like 1 millimeter, although it was tested by a laser to make sure everything was in position, unfortunately the laser was bouncing off a little bit of exposed metal where some paint had flaked away, and the error was not noticed. So the null corrector was wrong, therefore the test rig was wrong, therefore the hyperbolic mirror was made with a test rig which was telling it the wrong things. A much simpler test would have revealed the fault, but a simpler test was deemed to be unnecessary by Perkin-Elmer because their very sophisticated test rig said that everything was fine. The backup mirror was made and tested independently by Kodak, so if it was independently tested, it presumably would not have suffered from the same problem. But the backup mirror is on the ground, and the Perkin-Elmer mirror is in orbit. A bit of a quandary. Various things were thought about in terms of how do we fix this, but the one thing that saved it from a complete and utter disaster was the fact that it was designed to be serviced by shuttle astronauts. It was thought, do we send the shuttle up, pick up the Hubble, bring it back down to Earth again, hope it survives the re-entry, and then take the mirror out and start again, not quite from scratch, either start again by regrinding the mirror or start again from the Kodak backup. That would have taken quite a while to sort out. But what was realised was, well, actually we have a non-flight copy of the camera that's being used in the shuttle on the ground. That is quite common, to have a flight version of an instrument and a non-flight version of the instrument, so that if you have problems whilst it's in orbit, you can check out the one on the ground. So effectively, you've got a duplicate of the camera sitting on the ground. By checking what had gone wrong at Perkin-Elmer and realising that there was an error in the test rig, they knew how far the test rig was out of alignment, so they knew precisely how wrong the mirror was. It was the wrong shape, but they knew precisely what the actual shape of the mirror was. So they could say, well, if we know the mirror is the wrong shape, why don't we put a bit of corrective optics, a pair of glasses if you like, inside this camera that's sitting on the ground, such that it will correct for the error that we know is in the mirror, and then we put this camera in the shuttle. We get the astronauts to take this one up and put it in the Hubble Space Telescope. Then we will fix the problem for this particular camera. Well, that's one way of dealing with it, but what about the other instruments? There's more than one camera in the Hubble Space Telescope. It was decided to put an instrument called COSTAR, a set of corrective optics for all the other instruments. Room would have to be found for this, so one instrument that's already up there would have to be sacrificed in order to get this so-called COSTAR in position. It's perhaps not so obvious what COSTAR is, so there's a little model of it on the right-hand side. COSTAR is effectively a set of mirrors which are on arms that can be instructed to move into position. So if you wanted to send light to a particular instrument, then a particular arm would deploy and the light would be reflected off the mirrors into the particular instrument. And depending on which instrument you want to send the light to, you would deploy that particular arm. And the mirrors on the end of these arms would be figured to precisely the right shape to correct for the error that is in the Hubble's main mirror. So that's the idea. Sacrifice one instrument, replace it with this Swiss Army knife of mirrors that will provide all of the corrective optics for the other instruments. The camera will have its own, this will deal with all the other instruments that are on board. And when you think about the Hubble, it's tempting to think of the Hubble as just being a large camera, a large telescope with a camera on the back end. But at any given time, the Hubble has had at least 2 cameras and 2 spectrographs on board. These have been swapped out and upgraded during the various service missions spread over 16 years, and I'll say a word about that in just a moment. But when we think about the Hubble, we think about the camera that's being taken up to correct for the error in the main mirror, the chip in the largest camera, the most sophisticated camera that the Hubble has. The chip is this size, 4 by 4 centimeters. It's perhaps not much larger than the chip you might have in your digital SLR camera perhaps, which again would be a few centimeters by a few centimeters. So the chip is not that large, 16 megapixels in the final version of the camera. But the focal length of the Hubble telescope can be anything up to 58 meters. So if you imagine that's the size of the chip and imagine effectively a telephoto lens of 58 meters focal length, you can see that the field of view of the camera is actually quite small. The camera appears to be quite large, but the chip inside is not that large. Let's just blow up the picture we've got here. Remember, the telescope itself is not running the full length of what we would call the spacecraft. The main mirror, the primary mirror, is here, about 1/3 of the way from one end, and the secondary mirror is about 1/3 of the way from the other end. In a sense, you've got a large amount of nothing at the front, which is acting like a lens hood, a lens shield, if you like, to keep the sun out of the telescope. So secondary mirror, primary mirror, most of the instruments are sitting either on the side or simply behind the main mirror, and so the Swiss Army knife of COSTAR will send the light to whichever instrument wants to receive it. Let's have a look at how the Hubble was serviced. I don't want to make this too technical, but I think it's useful to remind ourselves just what a complex instrument the Hubble Space Telescope is. It was launched in 1990, and I've taken this timeline up to 2020. The first service mission was a few years after 1990, where camera 1 was replaced with camera 2. So the camera 1 was replaced with the camera 2, which was sitting on the ground, and this is the one that has the corrective optics built into it, so hopefully camera 2 should produce nice sharp images. The second bar here is an instrument that had to be sacrificed to make room for COSTAR, the corrective optics, the Swiss Army knife that then will give corrected light to all the other instruments. The asterisks that I've shown on the next 2 bars indicates that while they were there, the shuttle astronauts tweaked the gyros and the electrical systems. The gyros are responsible for making sure the Hubble points to the object of interest and stays rigidly pointing to that object during the exposures. Otherwise, of course, the images would blur. The next shuttle mission 2, replaced 2 of these instruments shown near the bottom here. I'm not going to deal with the details of what they are. Any instrument that has an acronym that ends with an S is probably a spectrometer. Anything that ends in a C is probably a camera. Let's not worry about the details. But here we see that 2 spectrometers have been swapped out for 2 different spectrometers. Why on the second shuttle mission would you replace 2 spectrometers so early? Well, remember, it's not that early. The Hubble Space Telescope was designed in the 70s and built in the 80s. Here we are at 1997. It's already old. Technology has moved on, and so it was possible to replace those spectrometers with better, higher resolution spectrometers. So that's what was done in the late 1990s. Near 2000, in a 1999 service mission, Shuttle Mission 3, made a little tweak to the gyros. There were a few problems with the gyros, and they had to make sure all the gyros were operating effectively. But shortly after that service mission, there was a little bit of a problem. The grey area seen at the bottom here, this grey indicates that that particular instrument started to give them problems. And in the fourth service mission 3B, again they tweaked some of the electrical systems and they fixed that particular niggling problem with the spectrometer. And then you see the final bar at the bottom there, they replaced a camera with, okay, ACS looks like a spectrometer, but no, that's just NASA being silly. That's actually a camera, so it's actually the advanced camera for surveys. So they've replaced that camera with another camera. They've upgraded the camera. So now every piece of instrumentation that originally was launched in 1990, every piece of instrumentation has now been replaced with a new instrument which has got all of the corrective optics needed to make sure that instrument works perfectly with the mirror, the primary mirror, as it is. That means you no longer need COSTAR, but unfortunately it's there. Then the question is, do we need a fifth service mission? It would be a lot cheaper to say we don't actually need one, but after a few years it was realised that some electrical systems were failing, one spectrometer started to give a problem and one of the cameras started to give a problem. So it was agreed that there would be one final service mission before the shuttles go out of commission. So in 2009, camera 2 was replaced with camera 3. In other words, there was another upgrade simply because, again, technology marches on. You can now get cameras with higher pixel resolution, and therefore the final camera 3 had a 16 megapixel camera. COSTAR is no longer needed because all of the instruments now have their own corrective optics, so this COSTAR has now done its job, and so it was replaced with a more useful device, another spectrometer. And everything was given a spring clean and a tidy up. The gyros, the electrical systems, and all of the other spectrometers and cameras were tuned to make sure they are all operating correctly. And as far as we can tell, that has been the case for the last few years. Yes, there were some scares a few months ago when they had a problem with one of the computers, but generally speaking, everything is now ticking over nicely. 2 cameras and 3 spectrometers are in use at the moment on the Hubble Space Telescope. So how has the Hubble contributed to our understanding of how the universe came to be and how the universe exists at the moment and how it works? There are, of course, way too many examples to give, so I'm just going to pick out a few things out of the list of things that I could possibly give as what has the Hubble done for us. So one aspect that Hubble has contributed to is getting an idea of how big the universe is, literally the size, and hence, given that we know how it's expanding, if we know the size, we can work out the age of the universe. And one of the ways it did that was to look at, this image might look like a little bit of the Milky Way, but actually it's a little bit of the Andromeda galaxy. And because of the fantastic resolution of the Hubble Space Telescope, it's possible to see individual stars in distant galaxies. Some of these stars are called Cephids, which are particular types of stars which are bright enough to be seen in distant galaxies and have a variation in luminosity where the period of variation is determined by their absolute luminosity, how bright they actually are. So if we see some of these Cephids in other galaxies, by looking at how they vary in time, we can convert that luminosity variation period to an actual luminosity. And if we compare how bright they are with how bright they look in the images we've taken, we can gauge the distance to the galaxy in which those stars are sitting. And hence the Hubble, by doing this with our local galaxies and some of the galaxies that are close enough to see individual stars, the Hubble Space Telescope was able to measure distances to the neighbouring galaxies. And by getting that yardstick of if we know how far it is to this galaxy and if we know its redshift, then we know how far it is to more distant galaxies, we can get the overall scale of the universe. And that helps us understand the Hubble parameter, how fast galaxies are receding at a given distance, and it also helps us gauge the age of the universe. It's sobering to remind ourselves that prior to Hubble, we weren't actually sure what the age of the universe was. We weren't sure what the Hubble constant was, how fast the universe is expanding. And the Hubble, in its early days, back in the 1990s, helped pin those numbers down. It's also difficult to remember sometimes that when we're talking about exoplanets, because satellites like Kepler have found thousands of planets around other stars, again it's sobering to remind ourselves that back in the 1990s not much was known about exoplanets. And the Hubble was one of the telescopes that had the resolution of actually being able to image an exoplanet. Here we see the dusty region around a star, and the star itself at the centre of the image has been blacked out. The little dot there shows you where the star would be, but the star is so bright we have to black it out in order to see anything at all. And within that dusty torus around this particular star, if we look at the inset, we find a planet that's orbiting and a planet that's changed its position from 2004 to 2006 as it has its long orbit around its parent star. So there are other ways of finding exoplanets, but there are very few telescopes that can actually image exoplanets directly. Not only that, but you can start to think about, well, can we take the spectra from a planet? And again, that's why the Hubble Space Telescope has got spectrometers on board as well as cameras. Cameras tell you what something looks like, but spectrometers will tell you what it's made of or what it's doing. And so, for instance, it was possible to measure the water abundance on exoplanets to give us an idea of how many exoplanets might be the places where water exists and hence the places where life might exist. The Hubble Space Telescope must have imaged I don't know how many thousands of galaxies in the 30+ years that it's been operating. But because it has such fantastic resolution, by imaging nearby galaxies, we can get a huge amount of information about galaxy structure, and from that we can infer galaxy evolution, which tells us about how the universe, more generally, has evolved. Different structures, not only the familiar ones of galaxies with spiral arms, but galaxies such as this, trying to understand how these galaxies came to be. When we look at galaxy clusters, we often find a very interesting phenomena called gravitational lensing. Here, what we see is a distant galaxy shown in the inset here, a distant galaxy which has got a little bit of a bluish colour, and there happens to be a more foreground galaxy, which looks a little bit orange in this image, that happens to lie on a line of sight between the distant galaxy and us. And that is bending the light and causing distortions, including multiple images of this same galaxy. So this galaxy shown in the inset is actually the same as this galaxy here in the upper right. And it's actually the same as this galaxy imaged up here. So not only can we multiply image a given galaxy, what we've seen here is that we have 4 very bright points of light within this single galaxy image. And we can ask ourselves, is it very likely that we have 4 supernovae going off at the same time and catching them in this image? Given that a supernova is only likely to happen something like once every 100 years in any given galaxy, it seems very unlikely that we've caught by coincidence 4 supernovae going off at the same time. And it's been determined that these are actually the same supernova that have been imaged multiple times. So what I mean by that is, if we imagine that we are in the bottom left and this distant galaxy is in the top right, light has taken different paths to reach us, and hence we get different versions of the image, because the light is being lensed by the large mass of this galaxy cluster sitting in between us and the distant galaxy. This large mass, if you like, distorts space, and then light follows the distortion of space, and it produces this so-called gravitational lensing effect. It's useful to know how much mass is there, and when we calculate how much mass do we actually need to produce this amount of bending of light, it turns out the mass we need is far more than we can account for simply by looking at all the galaxies that seem to be in this galaxy cluster. This is one of the pieces of evidence that dark matter exists, because we get gravitational lensing which is much stronger than we would expect if it was only the visible matter that was producing the gravitational lensing. So in this particular case, observing the same supernova 4 times was quite interesting. But because the theorists could say to themselves, well, if we look at the paths taken by the light, we can predict that although the light will come via these various routes on going through this gravitational lens, we reckon that this one is longer by a few months in terms of how long it will take light to reach us. If it has to take this somewhat more of a dogleg to reach us, the light has a greater distance to travel, so the light will take longer to reach us. So although we see the 4 supernova in this galaxy here, we do not appear to see the supernova in this galaxy. But it was predicted that because the light is taking longer to reach us via that route, if we roughly know when the supernova took place in this inset, we can calculate that we would expect the supernova to go off in that other image in, I can't remember, 9 months' time or whatever the prediction was. So Hubble went back and imaged that galaxy again 7 months later, 8 months later, 9 months later, and yes, the supernova did appear in that galaxy. So the idea of being able to predict something that's going to happen because of the different length of time light takes to reach us, I think is quite an incredible result. And perhaps we're all familiar with the idea of the Hubble deep field, this iconic picture of take a picture of nothing in particular, find a bit of empty sky and expose for something like 1 million seconds, about 10 days or so. And this particular image has, I think, 2 or 3 stars in it. You can see the stars in the Milky Way. These are the objects with these little spikes on them that we can see here. I think there were only 3 of them. Every other object in that field of view is a galaxy. So there were many thousands of galaxies in this, remember, small field of view. Remember, it's small because we have a relatively small chip with a very long focal length. And we're looking back a long way in time. Because we are looking at galaxies that are many billions of light years distant, we are looking at them as they were many billions of years ago. And it's thought that the look back time for this particular image would be perhaps of order 13 billion years. Remember, the universe is 13.8 billion years old. So we're getting a long way back to the Big Bang in images such as this. And to show it's not a fluke, an image was taken in the southern hemisphere as well. This is just a reminder of the scale we're talking about. When you have a small chip and a 58-meter focal length, the field of view is indicated by that red rectangle there compared to the size of the moon, just to give it a sense of scale. A slightly longer exposure was taken in the southern hemisphere to go a little bit further back in time, a little bit further back in space, and also just to show that yes, the universe does look the same in all directions. We expect the universe to be isotropic. We wouldn't expect looking to the left to be fundamentally different from looking to the right when we look out to the universe. And again, although the details are different, the distribution of galaxies look pretty much the same when we look in the southern hemisphere. The Hubble Space Telescope has taken a number of images, such as this one, where again we're looking at a cluster of galaxies, the more orangey objects in this field of view, and the more distant objects, which are these somewhat more bluer spiral galaxies. I hope you can see some of the detail. These more distant objects can look very distorted. Some of the galaxies look undistorted and look like small spiral galaxies, but some of them get distorted into lines or arcs as the light travels through the gravitational lensing effect of this cluster. So these various faint arcs in the background can be analysed to give us information about the mass that is producing this distortion of the light, the more distant light, and that is one of the fundamental pieces of evidence that tell us that the universe appears to be chock full of dark matter. There is more dark matter out there than there is visible matter, than there is ordinary matter. And the Hubble was instrumental in giving us that evidence, which has now been backed up by much more evidence from other telescopes that have come online. In addition to the scientific legacy, which is undeniable, the Hubble Space Telescope is one of the few scientific instruments that's actually managed to bring the public along for the ride. There are not many scientific instruments that the lay public will understand and identify when you show them and understand what they have done. The laws of physics have created these incredible structures, whether they be nebula or galaxies, and the Hubble has revealed them, it's been said. Through all the research, Hubble has brought the public along for the ride. It's taken the excitement that scientists feel with new discoveries and brought it to non-scientists. That was a quote from 2015, the 25th anniversary of the Hubble. So let's just take a few minutes and indulge ourselves with some of the wonderful images that the Hubble has produced, and these are simply some of my favourites. The Helix Nebula, which is visible low down in the south as seen from England in the constellation of Aquarius, but of course we can't see it in this exquisite detail that the Hubble has managed. All of the detail within this planetary nebula, an atmosphere of a star that was blown off many thousands of years ago. Some of the detail that the Hubble has been able to show us of colliding galaxies has been phenomenal. Here we see the antenna galaxies, and we can see these two galaxies in the process of collision, and all of the pink regions that we can see here are hydrogen regions that are riotous star-forming regions. So collisions of galaxies is by no means the end of life of galaxies. On the contrary, in many cases it is the emphasis of new life. It is the new life that comes from star-forming regions that are prompted by the collisions of the galaxies. And indeed, we think that's how galaxies evolve, is through collisions like this. The Crab Nebula, familiar to us in the past, but the exquisite resolution of the Hubble Space Telescope has been able to tell us what sort of detail we can see in this supernova remnant, and by taking images a few years apart, it's been possible to see how this nebula has been expanding since the supernova went off back in 1054. Mystic Mountain is part of the Eta Carina Nebula in the southern hemisphere, and it's one of these pictures of a nebula in which you have a star-forming region, and some of the very hot stars within the nebula are producing stellar winds which are sculpting the gas around them into these wonderful structures. This particular one is called Mystic Mountain from the Eta Carina Nebula. One of my favourite galaxies is the Sombrero Galaxy, Messier 104. So you get this beautiful dust lane around the rim, around the equator as it were, of the galaxy, and the central bulge is not so well defined, but it just throws into stark contrast the dusty regions around the rim of the galaxy. Here we see part of a globular cluster, and one of the things that Hubble is able to do that some telescopes fail to do is to resolve stars all the way into the core of the cluster. In many cases, telescopes have been able to study globular clusters only by looking at the stars away from the centre, because the stars are so heavily packed, so densely concentrated in the core of a globular cluster that they often overlap. Whereas the Hubble has the spatial resolution to be able to resolve individual stars even down into the core of a globular cluster. There are, of course, wonderful spiral galaxies. This one happens to be a spiral, a barred spiral with a very prominent bar and two very large spiral arms. But by studying thousands of different galaxies with different structures, we get a better idea of galaxy evolution. And another example of interacting galaxies, these ones not necessarily in the process of collision, but certainly interacting with each other in the sense that the gravity from one is interfering with the spiral arms of the other. Even more than the crab, I think this is a wonderful image of a supernova remnant, because it's a part of the Veil Nebula. The Veil Nebula is very large in the sense of within our skies. It's about 3 degrees or so across, and of course you can't get all of that into a Hubble image, but by concentrating on a little part of the shock waves that are produced by this supernova material being thrown off from the supernova and expanding into the interstellar medium, you get an idea of the structure. Not only the structure, but by breaking it down into the colours. Here the colours are representative of what the hydrogen is doing, what the oxygen is doing, what the sulfur is doing. By taking images at different wavelengths corresponding to the light emitted by different atoms, we get an idea of the chemical composition as well as the physical structure of the shock wave produced by a supernova. Quite an amazing image. And of course, the pillars of creation, I guess we can't ignore that. It was taken as an image back in the 90s and then re-imaged in the 25th anniversary after it had obtained its final version of the camera with the highest possible resolution, so a slightly larger field of view and a higher resolution, the pillars of creation in the Eagle Nebula in the Northern Hemisphere. Excuse me, as visible from the Northern Hemisphere. So some amateurs have taken images similar to this one, again imaged in different light to highlight the hydrogen, the oxygen and the sulfur content of these gas pillars that are being sculpted by very hot stars. And again, just to remind ourselves that the Hubble Deep Field or the Ultra Deep Field have revolutionized our idea of exactly what is out there. If you get a few thousand images in a picture that's only looking at a tiny picture of sky, you realize that there must be at least 1 trillion galaxies in the observable universe. So what lies beyond Hubble? Yes, ground-based telescopes are fantastic. Ground-based telescopes can have much larger mirrors. And ground-based telescopes can use adaptive optics to try and compensate for the turbulence of the Earth's atmosphere. For instance, like in the image on the left here, you can shine a laser into the sky to produce an artificial star many kilometers up in the atmosphere, and that artificial star will give you an idea of how the turbulent Earth's atmosphere is affecting the images you're trying to acquire. So if you can do that on the ground, by simply moving, well not simply, but by compensating for the turbulence of the atmosphere by making small adjustments to the position of your mirrors in your telescope, why do you need a space telescope? So for instance, if we look at the sizes again, the European Extremely Large Telescope on the right is absolutely huge compared to the Hubble Space Telescope in the bottom left. So why do we bother with the idea of space telescopes at all? Well, one point is that even with adaptive optics, ground-based telescopes can only achieve high resolution over a limited field of view. You can send a laser up here which tells you what the atmosphere is doing over here. But if your field of view is also covering something over there, then, well, that atmosphere is doing something different. So you would need multiple lasers scattered all over your image to tell you what the Earth's atmosphere is doing at various points in your field of view. So it's fantastic if you only want to know what's going on with this exoplanet. You just get yourself an artificial star, put it next door to the exoplanet, and that will give you very nice resolution. But if you want to get the entire field of view equally sharp, that is a problem with adaptive optics. And of course that is not a problem with a telescope which is above the Earth's atmosphere, where everything is clear regardless of looking at different parts of your field of view. So a space telescope should achieve the specified resolution, once you've got your optics right, over the entire field of view of the CCD chip in your detector. And that's not something you can say at the moment with adaptive optics of ground-based telescopes. Let's just remind ourselves about other telescopes that are in orbit or have been in orbit. Kepler had a very specific mission to find Earth-like planets orbiting other stars. And it did that with a very large detector. Remember, if you compare that with what's in the Hubble Space Telescope, you can see the detector in Kepler is huge by comparison. And that was used not to survey the sky, but to stare at one patch of sky. You can see it illustrated here. Perhaps you recognize Cygnus at the bottom of the image, and there's Vega and Lyra over to the right-hand side. So the idea was to stare at one patch of sky and monitor the brightness of stars and look for any stars that have a characteristic dip in their brightness, which indicates that an exoplanet in orbit around that star has transited and produced a dip in the light. And that's how thousands of planets have been found. Gaia is an ESA mission with very ambitious aims. The aim for Gaia, which is still in operation, is to measure the positions of some 1 billion stars or so down to a phenomenal accuracy of about 25 micro-arc seconds. So even compared to the resolution of the Hubble Space Telescope of milliarc seconds, that is quite incredible. The idea is to perform some spectral and photometric measurements, so that we can then map out where the stars are in the Milky Way and how they are moving. And that gives us an idea about the dynamics of how the Milky Way as an entity is changing. But basically the bottom line is, can we make a 3D model of the Milky Way by looking at where stars are and measuring their distances using parallax? So if we reflect on the Hubble Space Telescope, if you'll excuse the pun of a reflection of the Hubble Space Telescope, is there a successor waiting in the wings? And I'm sure none of you can have missed the fact that the James Webb Space Telescope should be launched in hopefully only a few weeks' time. Like the Hubble, it's had a checkered history. It's been waiting in the wings an awful long time. It was supposed to be launched many, many years ago, and there were various delays getting it ready for next month's launch. You see the relative sizes. The James Webb has got a mirror some 6 meters or so in diameter compared to the Hubble's 2.4 meters. So it's going to be segmented. You can see that it's very difficult to make one big mirror and get it up on the top of a rocket, so it's been made in segments and will unfold once it's finally in position, or actually it's going to be deployed on its way to its final resting place, which is going to be the so-called L2, Lagrangian number 2 point. You can see where Lagrangian number 2 is. Here's a little schematic of the Sun, the Earth, the Moon, and L2 is a point further away from the Earth than on the non-sunward side, on the night side of the Earth. If you go another 1,000,000 miles or so, you get to a point where you can park a spacecraft. In other words, it's a stable point, and the combined gravity of the Earth and the Sun make the L2 point go round in 1 year, which of course is the same length of time that the Earth goes round. So the L2 point always stays in the same relative point relative to the Earth. And you can park a spacecraft there. Gaia is currently at the L2 point, and the James Webb will be sent to the L2 point. James Webb is being sent out there to get it well away from the Earth and the Moon to avoid picking up the heat radiation from the Earth and from the Moon. Because the James Webb is going to be working primarily in the infrared part of the spectrum, it can't, unlike the Hubble Space Telescope, be in Earth orbit. Or at least if it was in Earth orbit, then anything it picked up would be dominated by the heat of the Earth, not by the infrared of the object that we're interested in. So the idea is to build a large sunscreen, a sun shield, and take it out to L2 and park it there and make sure that the sun shield is always between the telescope and the Earth, Moon and Sun to keep the telescope as cold as possible. But the problem with L2, as I'm sure you can appreciate, is it's very difficult to get to, and you can't simply send an astronaut up to fix it. So if it gets to L2 and starts operating and then there's a problem, there's really no option for fixing it or maintaining it. So what will the James Webb do once it's there and once it's operational? By working in the infrared, it should be able to see more than the Hubble. If we compare the pillars of creation taken in visible light with the same pillars of creation taken in infrared light, the Hubble Space Telescope was able to work a little bit into the infrared. It was mainly in the visible, but it just about overlaps a little bit with James Webb and so can produce infrared images. And that gives us a hint of what we can expect with the James Webb. Because if we look at the pillars of creation on the left, we can see a very dusty environment with all of these gas pillars being sculpted by the stars. But if we look at infrared, we can see inside those pillars and we can see what's going on. Note how many stars are visible on the right compared to the left. Those stars should be visible, but are extinguished by all of the scattering through this gassy, dusty environment that we can see there. So it will be possible to look and see early stages of star formation in these very dusty environments. So stellar formation is one aspect that the James Webb will be able to do for us, but also when we're looking at exoplanets that are in the process of formation around stars, again a very dusty environment. It's very difficult with optical telescopes working in the visible part of the spectrum to see exoplanets in the process of formation. But infrared will be able to cut through a lot of that dusty environment and be able to tell us what's going on. So stellar formation and planetary formation will be something the James Webb will be able to excel at. Not only that, but when it comes to what I guess will be the James Webb Deep Field, I'm sure they will do something similar to the Hubble Deep Field. Remember, these objects we're looking at are very distant. We're looking back in time, a long way back in time, at objects that are a long way from us. And because of the expansion of the universe, they are moving away from us, they are receding from us at very high velocities. Some of these galaxies might be receding from us at more than the speed of light, for instance. And so the light from these distant objects gets stretched and reddened, and this is called a redshift. So the light that might have been emitted as ultraviolet light or visible light by the galaxy, because of the expansion of the universe, this gets pushed to the red end of the spectrum and can end up getting pushed all the way into the infrared. So galaxies that would otherwise be quite bright in the visible part of the spectrum, when they're receding from us very, very fast, tend to look rather dim, and the Hubble is struggling to see some of these distant galaxies. But we think they will appear much brighter in the infrared because of their large redshift. So that means some of these galaxies will look brighter when looked at in infrared, and it will also mean that we might be able to see further because we will be able to see more distant galaxies which simply don't show up in the visible part of the spectrum. So the James Webb ought to be able to see further and hence further back in time. So if the Hubble Space Telescope can see back perhaps 13 billion years, it's hoped that the James Webb will be able to look back 13.5 billion years, even closer to the 13.8 billion years back to the start of the universe in the Big Bang. So I've given you an introduction to the need for space telescopes and why ground-based alternatives are fantastic, but not necessarily a replacement for space-based telescopes. I told you how the mirror was flawed and how it was fixed, and I've given you a taste of some of the science and some of the beautiful images that the Hubble has produced. And I hope I've convinced you that although ground-based alternatives are fantastic, there will always be a need for space-based telescopes. Thank you for listening.